Hey everyone, welcome back to our series entitled Subnetting Demystified. This is the second presentation in our series. The first presentation was an introduction where we laid out a roadmap of where we want to go, and that roadmap consists of the points that are shown up on the whiteboard now. And where we're going to start is with this first topic entitled IP addressing. Now, this may be a bit of a review for some of you, but I think it's a good idea for us to all get started on the same page and talk a little bit about what is IP addressing and where does this concept of an IP address fit within the larger picture of networking, which will eventually lead us up to the topic of subnetting. Let's take a quick look back at the OSI 7-layer model. When we're talking about IP addressing and subnetting and routing and all of the sorts of things that we're going to cover in this presentation, these are occurring at layer 3, or the network layer. The Internet Protocol, or IP, is a layer 3 protocol, and underneath that we've got the data link layer, layer 2. This is where Ethernet lives. This is the land of MAC addresses and network broadcasts and that sort of thing. And of course underneath that we've got the physical layer, which is cables and connectors and pin configurations and voltage levels and so forth. So that's just to put this into the perspective of the OSI 7-layer model. We're going to be working at the network layer, layer 3, which is directly above the data link layer, layer 2, and directly below the transport layer, which is layer 4. Here we have a simple network topology that we'll be using in this presentation as well as some of the others in the series. And you can see that we've got a few devices connected together. These are routers, and they're connected together probably with some sort of wide area network connectivity. It doesn't really matter. They're connected each one to the other. Let's just assume this is a wide area network of some sort. And on the other side of each of these routers, we've got a local area network consisting of a number of computers connected to the local area network side of each of these routers. So to put this into a real world perspective, you might imagine this as an organization that's got 3 locations. Each location is connected to the other 2 using a wide area network connectivity of some kind or another, and each location also has a number of computers and servers and printers and so forth in the local area network of each office. So that sort of sets the stage of this network topology that we're looking at here. So when we're talking about connectivity within the local area network, we're really focusing on layer 2 here. If we have one of the computers here in the local area network of location number 1 that needs to connect to another, that's largely a layer 2 function, and this communication is built upon broadcast domains with broadcast messages being sent within the domain. So this is a broadcast domain right here. This is a layer 2 broadcast domain that within which any one of these computers can easily communicate with the other without having to involve the router or anything having to do with the wide area network. Now that picture changes if we have one of these computers here needing to communicate with another one of the computers in the local area network of one of the other locations. And if that's the case, if we have this first computer here in location 1 that needs to connect to this first computer over in location 2, then layer 2 broadcasts are not going to help us here because layer 2 broadcasts are bounded by the local area network. So if we want to get traffic from this computer here to basically any of the other computers in any of the other locations, we're going to have to invoke the assistance of one of the network routers to help find the best path through this network to deliver the traffic to its ultimate location. And that's really the main thing about layer 3. It's involved with path selection. Notice here we've got a couple of potential paths that we could follow to get from any one of these networks to any other. We could go from here to here to here and to here directly, but also we could conceivably go from here to over here and then back here and up there. So we've got multiple paths through this network, and layer 3 is concerned with selecting the best path and then moving traffic through that path to its ultimate destination. And that's what happens at layer 3. Layer 3 is the layer at which network routing takes place, and that's that process that I just described here where we're finding the best path through the network, and then at each stop along the way we're forwarding the traffic in the direction that is the closest next stop to get to its ultimate destination. And that's what layer 3 is all about. You've probably already heard an analogy between layer 3 and IP addressing and your street address, and that analogy holds up pretty well. And just like the Postal Service would have a really hard time delivering mail if there were duplicate street addresses, the same thing is true with the layer 3 network. Each of these devices that's going to have connectivity to this network at layer 3 is going to have its unique identity, or it's going to have its own unique identity within the context of the broader network. So just as your street address is unique within your geographical area, then each of these devices here in this network is going to have some unique identity within the context of this network, and that unique identity is something that we call an IP address, or an Internet Protocol address. Okay, we've been talking about IP addresses, so it's now time that we actually got a chance to look and see what does an IP address look like. Well, this thing that I've written right down here at the bottom of the screen, there's an IP address, and that should be read as 192.168.10.2. And notice that this consists of 4 numbers separated by decimal points, or dots. And when we see an IP address written in this way, we refer to this as dotted decimal notation. I've also written out IP addresses for each of the computers connected to the local area networks in our topology. And the way I've done that is something that you'll often see done when you're interpreting network topology diagrams. So let me explain to you what's going on here. Up here at the top, notice that I've written 192.168.10.x. And down below, you can probably see where this is going. I've identified the workstations as 2, 3, and 4. So the way we should read this would be to say 192.168.10.2. That's the IP address for the first workstation in location number 1 here. And 192.168.10.3, that's the IP address for the next workstation here in the middle. And the last one down at the bottom is going to be 192.168.10.4. Well, why do we do that? Well, the reason that we do it this way, or the reason that I've done this topology this way, is that it just tends to clutter the diagram up a lot less if I do this little bit of abbreviation, because if I had to write out 192.168.10.2 and then 192.168.10.3 and 192.168.10.4, I'd have to write it so small you wouldn't be able to see it, and it tends to clutter up the diagram. So I've just chosen to do it this way. So just know that that .x is going to be replaced with a .2, .3, and .4 for each of the workstations. And you can look up here at location 2, and you can see that I've written it out in a similar way, 192.168.20.x, and that would be interpreted as having this first workstation with an IP address of 192.168.20.2. The next one would be 192.168.20.3 and 192.168.20.4. And then we've got exactly the same thing going on over here at location number 3 over here on the other side. So let's think back to that analogy that I made just a few minutes ago when we were talking about your street address and how that is similar in a number of ways to an IP address. Your street address has got a number that identifies your house, and then the rest of the address identifies the street where your house is. And if we examine the IP addresses in this network topology diagram that I've drawn here, we can just sort of look at it, and probably intuitively you can figure out what's going on here. Notice that all of the computers in each of these 3 locations, with respect to their IP addresses, they have certain elements in common. If we look here at this location number 1 here, we can see that all 3 of these computers have an IP address that begins with 192.168.10, and then only the last number changes. The same thing is true for this second location here at the top. They all have 192.168.20. something, and the only thing that changes is the last number, and the same thing is going on over here at location 3. So sort of intuitively we can begin to think about the fact that this IP address could be interpreted to contain 2 pieces of information. One piece of information could tell us, or does tell us, about the network that each of these computers is attached to, and then that last number that I've represented with a placeholder X here identifies the specific computer within that network. So we sort of split this IP address into a couple of parts, and I'm just going to draw a line right through there to identify that the first part, of this IP address identifies the network to which these three computers are attached, and the last part of the IP address refers to the specific computer that is attached to the network. And we've got the same thing happening here and the same thing happening over here. So from that we can sort of deduce that an IP address has two parts. The first part we call the network address, and then the last part we call the host address, and there's a dividing line that separates where the host address portion stops and the network address portion begins. I should also mention that even though I have not drawn on the diagram IP addresses for each of these routers, they certainly are going to have IP addresses just like the computers do. In fact, where each of these computers has only a single IP address, these routers are going to have multiple IP addresses. They're going to have an IP address at each point that they connect to the network. Now that's starting to get a little bit out of the scope of our discussion here. So rather than actually draw the IP addresses in, I'm just going to make a few X marks here to note the fact that router 1, it would have to have an IP address configured to each point at which it connects to another network, and we call those connection points interfaces. So router 1, it would have an IP address on the interface that connects to the local area network over here. Router 1 would also have an IP address on this interface which connects to the wide area network going up this way to router 2, and it would have yet another IP address on this interface that connects router 1 with router 3. And the exact same thing would be true of the other routers as well. So just to simplify our discussion, I'm going to leave these IP addresses out of the picture for right now, but I'm just going to put X's to mark the spots where those IP addresses would be configured in a functioning network. There are a number of different, I'll call them rules, I suppose, for assigning IP addresses. You may wonder, well, why 192.168 for these IP addresses? Well, there's certainly a method behind the madness there, and that's going to be the topic of future presentations. But the takeaway for this presentation is to first keep in perspective that we're talking about layer 3, and the function of layer 3 is the selection of a path through a series of connected networks and finding the best path through the topology. And also keep in mind that each device that's connected to a layer 3 network is going to have its own unique identity, and at layer 3 we call that identity an IP address or an Internet Protocol address. The protocol that we most often discuss at layer 3 is the Internet Protocol, or IP, and the IP addresses are what you see drawn on the diagram here. So as we go into our next presentations, we're going to talk more about these IP addresses and exactly how do we know where the dividing line between the network and the host occurs. There are two final points that I'd like to make before we wrap up this presentation on IP addressing, and the first is this. If you look up here at the top, you'll see something that by now is familiar because we've been pondering these for a bit now. Up here at the top, this is an IP address written in dotted decimal notation. This would be read 192.168.20.1. And as humans, this is comfortable for us to interpret and to read and describe because it uses the decimal numbering system that we're all familiar with. So we have these 4 decimal numbers separated by periods or dots. But what the computer sees internally is a 32-bit binary value. What do we mean by that? Well, if we consider that each one of these decimal notations is represented internally with an 8-bit byte, if we take 4 8-bit bytes and add up all of the binary decimal positions, we'll wind up with a binary number that's 32 bits in length. And here I have written out the binary numbers that are equivalent to the decimal numbers that you see above. And if you were to count all of these out, you would see that there are 8 binary positions here that represent this octet. There are 8 more binary positions here that represent this second octet here. And then there are 8 more for this octet, and then finally 8 for that one. So that's going to sort of lead us into our next presentation, which is going to be dealing with binary math. How do we get from here to here? How do we do this conversion? How can we take the decimal number of 168 and wind up with 10101000. How do we do that? Well, that's what we're going to take up in our next presentation. And the final point that I want to make regards the dividing line between the network portion of an IP address and the host portion of an IP address. You'll recall from our earlier discussions, we said that an IP address always consists of two pieces of information. Information about the network and then information about the host that's attached to the network. And we have a dividing line somewhere in this IP address that represents the network portion, or that divides the network portion of the IP address from the host portion. And in our example, we said that the dividing line is right here. So how do we express that? Well, the way that we express that, there are a couple of ways, but I want to tell you about one way right now. And you've probably seen this if you've ever configured an IP address on a device or seen a device that had an IP address configured on it already, is that we always see an IP address and something called a network mask together. So anytime you put an IP address on a workstation, if you're configuring it manually, you'll see the IP address, and then right underneath that you'll see something called a mask. Occasionally it's referred to as a subnet mask. There's a subtle difference that makes it correct in some situations to call it a network mask, and in other situations to call it a subnetwork mask or subnet mask. We'll get into that later on. But it looks something like this: 255.255.255.0. So where the digits stop and turn to zeros, then that's where the dividing line is, right here. So if we were to convert these 255s into binary, we would see that this is going to be 1111111111.1111.0000000. So that's what the binary representation of a subnet mask or a network mask looks like. And where the ones stop and the zeros start, that marks the dividing line between the network portion and the host portion of any IP address. So that gives us a segue into our next presentation, which is going to be discussing binary math. And also we're going to talk about a couple of different ways that we determine where this dividing line falls, separating the network portion of the IP address from the host portion. Okay, well, that wraps up this video. Thanks for tuning in, and be sure and check out our next presentation in this series, where we're going to take up the topic of binary math.